So this chapter section is going to look at change in population, so population growth, using the exponential growth model. So when we look at population change, there were four things: births and immigrants that add to the population, and then deaths and emigrants, which detract or remove from the population. Most of the time, it's really hard to measure immigration and emigration. And a lot of the time, immigration and emigration, even when they can be measured, are not necessarily the main drivers of population change. So as a scientist studying a population, I might ignore these two. And then the equation comes down to just births minus deaths. And I know that your book does go into the math on this, and we are not going to do that. We did Hardy-Weinberg, and that was enough. So we're going to look at the overall graphs, but we're not going to actually do any population size equations calculations. So overall, the size of the population is going to mostly be births and deaths. You can do some calculus here to get to an equation, but eventually we have something called a growth rate. And exponential growth is what happens when this grows exponentially. And this creates what's called a J-shaped curve, like this. So exponential growth happens very slowly at the beginning. So if something is doubling, that would be exponential growth, right? From 1 to 2 to 4 to 8 to 16. So that's kind of this low end of this curve. And then if you've ever counted things that double, 32, 64, these start to really increase, and then this takes off very quickly. So that's an exponential growth rate. On here you can see two different populations, so they're both going to start here at the same number of individuals at the beginning. Capital N is the population size at any time, and what this means for those of you who have not had calculus, dn is the change in size, and then dt is the change over time. So the growth rate is the change in the number of individuals over the change in the amount of time. Okay, so what we can see is starting at time, we're going to measure time in the number of generations rather than years, because some species will grow faster just because they have shorter generation times. So if we look at these two populations, this one has a growth rate of 1, and this one has a growth rate of 0.5. Which one's going to grow faster? The one with the higher growth rate. And so without doing all of the math, we can see that this is going to grow twice as fast as this group. So when the growth rate is higher, we see this exponential growth take off, and then this is going to grow, and look how fast these numbers get to very large, whereas this one, it took a little bit longer to get to kind of this explosive growth stage, but it's going to grow fairly quickly as well. If you're thinking, exponential sounds pretty familiar, that's because it has been in the news recently. So this is a New York Times article about the COVID outbreak, this is from way back in March. And this is one of the articles urging people to take precautions against spreading the disease. And part of the reason for this is because COVID-19 is not growing exponentially because it's not a living thing, but it is spreading exponentially. And so the more precautions we put in place, the slower that growth rate. If you prevent one case at day 10 versus preventing a case later on, that has a massive impact, because that one person prevented earlier in this pandemic results in a massive difference in the number of people infected because of the way that exponential growth works, because that one individual can double and double and double and double to spread the disease to many, many more people. So the growth curve doesn't look like this anymore. So this is the growth curve as of today, which is November 19th. And you can see that at the very beginning, it actually was exponential, and we're so zoomed out on this graph, you can't see it anymore. You can see it on the logarithmic. This was the exponential growth period. And now it's kind of growing, but it's not so much. And we're kind of reaching another spot here where it starts to look like another J. And the reason that it's not fully exponential is because we've taken precautions to limit the spread. So the wearing masks, staying home, social distancing, washing hands, but really mostly wearing masks and staying home, have prevented this from becoming that exponential growth that we're actually starting to see again here at the end, though. So here's an example. This is the African elephants in South Africa in a national park. And originally the population of elephants was extremely low. And after hunting was banned inside of this national park, those elephants no longer had that pressure on them. And so what started out as a really small population of elephants in about 1905 here has exploded. And I don't know the current data of this elephant population. But if you see that it kind of goes up slowly here, and you can track this as real life data along this J-shaped curve. And then at some point this curve kind of spins, and this is where the J comes up. And because this exponential growth rate is so high, it's going to massively increase. So the question about exponential growth of populations is, can this be sustained? Can these elephants continue to double in size over and over and over again? What's going to happen eventually when there's so many elephants that they fill up the national park?